Hi everyone. So remember, we just finished. We've pretty much talked about two different tests we can use so far to assess whether a series converges or diverges. The first of which we should always start, is called the test for divergence, because that tells us immediately whether a series is going to diverge. And if that's the case, we don't have to go through looking at all these other convergence tests we're going to learn. The second one is if the series looks like it's something called a p-series. And if it's a p-series, again, that's a very, very simple test, maybe a couple seconds for convergence or divergence. So if it's not a p-series, the next thing we want to look for is, does it take the form of something called a geometric series? So a geometric series, I've given them right here. Basically, it's a series that has terms that look like this, where these values a and r are some kind of constants. So realize that this series right here is actually identical to this series right here. But what we've changed is we've changed the starting place of the series. Instead of n equals 1, we go to n equals 0. And that means we change our power. But realize if you write out all the terms in this series, you're going to get this thing right here no matter what you do. So sometimes a geometric series is represented starting at n and having our constant r raised to the power n minus 1. Or other times it looks like this, where we start at n equals 0 and we raise r to, or our constant r to the value n instead of n minus 1. So basically, we always want to get it into one of these two forms. And if we can get it into those forms, if the absolute value of that constant r is less than 1, then the series converges to this really neat fraction right here, a over 1 minus r. Now, if you guys are curious as to how in the world that's possible, I'm not going to go over that derivation in this video, but just come see me during tutorial and I'll be more than happy to go over it with you. Also, if you're really curious as to some applications of geometric series, I'll go over those with you too. But here in these videos, I'm going to be a lot more concerned with just getting through the mechanics with you guys and not be so concerned about what the practical applications are. Though, in retrospect, those are, in my opinion, a little bit more important. But, I'm teaching an AP course. We got a lot of content to go over. I digress. Anyway, so let's get a little bit of practice in seeing whether we can represent series as geometric series, and furthermore, seeing if we can determine what they converge to. So take a look at this series that we have right down here. The first thing I want you to do is to determine, okay, is this thing a geometric series? And the next thing I want you to do is, if it's a geometric series, do we know what it converges to? So pause the video and give it a try. Okay, so if you've tried this one, well, this is a geometric series. We have a is equal to 1/3, and we have r is equal to 2. Notice that we start at n equals 1, and we have r raised to the n minus 1. So if we go back up here, it meets this form right there. So yes, it is a geometric series. However, our value for r is 2, which is not less than 1. So therefore, this is actually a divergent geometric series, but it is a geometric series. Okay? So, ready to try another one? All right, let's go for it. Let's look at this series here, okay? Again, pause the video, try to determine, is this a geometric series? And if it is, does it converge or diverge? If it converges, what does it converge to? Pause the video. Okay, so if you look at this one, again, we're given a series that meets this first form right here. We start with n is equal to 1, and we raise our constant r to the power n minus 1. In this case, our value for a is equal to 5. Whoa, that's a crazy looking arrow. Okay, that works. And r is 1/2. So in this case, absolute value of r is less than 1. So the series will actually converge to a over 1 minus r. And if we just plug in our values for a and r, we'll get that this series converges to the value of 10. All right, pretty simple. You think you're getting the hang of geometric series so far? All right, let me throw you a little curveball. All right, take a look at this one. Again, the first thing you want to do is ask yourself, is this a geometric series? Pause the video. So if you've given this a shot, well, is this a geometric series? It turns out this is a geometric series, but what some of you may have been looking at is, you're like, hey, hold on a second. We start with n equals 1, meaning we should raise our constant r to the power n minus 1. but we see right here we're actually raising it to the power n. So doesn't this mean this doesn't meet either of these forms of these series up here? And you are absolutely correct, it doesn't. However, we can actually manipulate this series so that it does match one of those forms. So if you said, no, this isn't a geometric series, we're done with this, try again and see if you can manipulate what's inside that series so that it meets one of those forms above. Okay, so if you tried this, again, what this is just talking about is that we have that difference in our n values. But check out right here. This is how we can, or one way at least, to rewrite this series. Okay, so some of you guys might be saying, hold on. How in the world is this thing equal to that thing? And the example I would like to say is, let's say we start with 2 cubed. Okay, that's a horrible looking 3. Let's make that better. There we go. All right, so if we have 2 cubed, can't we write 2 cubed as 2 times 2 squared? Well, if we do that, realize that we've just done exactly what we did in this series right here. Now, we had this thing starting at n equals 1, meaning we wanted to have an n minus 1 in this exponent. So to get an n minus 1, all we had to do was pull a 3/4 out, and therefore that power goes down. That's exactly what this thing is illustrating right here. That'll always work. It's a nifty little trick that we can use in a lot of analysis of series, not just in geometric series. So in this case now, we have a series that looks like this one, and we notice we start at n equals 1. Our constant r is raised to the power n minus 1, so everything works. We're great. In this case, both a and r are 3/4. Recall that a will be this front value, r will be this second value raised to the n minus 1. And since 3/4 is less than 1, the series does converge. It converges to a over 1 minus r, which if we plug in the values for a and r, we'll end up getting that it converges to the value 3. Now, there was actually another way we could have manipulated this series to get it into a geometric series, and this one is a little bit less intuitive, but pause the video and see if you can figure out how to do it. Okay, if you gave it a shot, we could have also rewritten this series as this. Okay, notice what we did. We started with n equals 1, and we said, okay, in our geometric series, going back up here, we either need to start with n equals 1 and be raised to the power n minus 1, or we can start at n equals 0 and be raised to the power n. So since we already had something raised to the power n, let's see if we can change this right here to be n equals 0 instead of n equals 1. Well, the way to do that is to just start it at n equals 0, but what we can do is, once we evaluate the entire series, just subtract that n equals 0 term from the entire series. That way it's going to go away, okay? So 3/4 raised to the 0, well, that's just equal to 1. So now we basically have a geometric series with a is equal to 1, r is equal to 3/4. We can find what that series converges to and then just subtract 1 from the final value. So in this case, if we do a over 1 minus r, we'll get 1 over 1 minus 3/4. But then again, if we subtract that 1, we end up getting a value of 3, which is exactly what we got up in here, and we should. So anyway, so a couple tricks, a couple ways that we can manipulate things that maybe look close to geometric series but not quite. If we kind of fool around with them sometimes, we can actually get them to be in the right form, and we can analyze them as geometric series. All right, you ready for another one? Let's try it. All right, try doing this one now. Okay, you know what you're supposed to do at this point. Pause the video. So if you try this one again, you know, some initial alarm bells should be going off, and you might say, wait, this isn't a geometric series because we have something raised to the n here and something raised to the n minus 1 right here. But remember what I showed you in the two previous examples. We can manipulate the way that we write these series to get them so they match one of these forms. Okay, so the way that I said is, okay, we got something to an n minus 1 up here, and we start at n equals 1. So let's see if we can switch this n to an n minus 1. Then if we were able to do that, we would be able to get something that was in the form of a geometric series. So if we do that, again, what we can do is we can just pull a 3 out of this term right here. Then that becomes 3 times 3 to the n minus 1. And therefore, we've just rewritten this series right here, but now it's in that form of a geometric series. We start with n equals 1, and it goes to the n minus 1. If you're confused how I went from 3 to the n to 3 times 3 to the n minus 1, remember, if I have 3 cubed, okay, just humor me and pretend that's a cubed up there, I can say that's just equal to, pull a 3 out, 3 times 3 squared. And that's exactly what I did right there. So instead of having a 3 up here, if I just have an n, we get 3 to the n would be equal to 3 times 3 to the n minus 1. So again, that's a nice little thing we can do to always manipulate these series so they match the form of a geometric series. In this case, our value of a is sine 1 over 3. Our value of r is 2/3. And since r is less than 1, the series converges to a over 1 minus r, which will just end up being sine 1. Okay? Now, we could have also solved this series by saying, okay, let's rewrite the series as this. Instead of changing this right here to an n minus 1, why don't we keep that as something to an n, but change the counter to start at n equals 0 and change that thing to be n minus 1. All right. So again, the way we can do that is we can do the same thing as we did up here. We can pull this 3 out. All right. But what we can do is just change where our counter starts in this case. All right. So, again, we're giving it the exact same series that we had before. We're giving it a series where a is equal to sine 1 over 3 and r is equal to 2/3. So this one will just converge to sine of 1 as well. It'll have the exact same value. But again, it's just about how can we manipulate our series so they represent the exact same series, but we just put them in a slightly different form. Okay, and what we did in this case was we did the same manipulation that we did in this step right here. But if we instead start at n equals 0 instead of n equals 1, what that makes is that this n minus 1 goes to an n instead. Because think about it, when n is equal to 1, n minus 1 will be 0. Well, isn't that the same thing of just saying, okay, well, let's just start at 0 and raise the thing to the n? If you don't believe me, look at this series right here and look at this series right here and just write out as many terms in those series as you can. You'll see that the terms are all identical in the exact same places. So those two series are actually the exact same thing. So again, just manipulating series. It's a very useful skill when evaluating geometric series. All right. So you guys have been following along with me so far right now. I commend you for that. Let's just try one more example. All right, now try this thing. Remember, determine, is it a geometric series? If it is, what does it converge to, or does it diverge? Okay, in this case, we actually don't have a geometric series, okay? We have a constant raised to the n minus 1. We start at n equals 1, so those n values are matching up to be in this form, which is good. But the problem is our value for a is this. And remember what we said, a needs to be a constant. In this case, a is not a constant. A is a function of n. So here, basically, a is not a constant, it's a function of n, so therefore this is not a geometric series, so we can't analyze this thing for convergence or divergence based on the criteria of a geometric series, okay? So hopefully what you're seeing with these videos is we're kind of just going through this step-by-step process of how we get, when we're presented with a series, how do we determine whether it converges or diverges? And again, to repeat, we always start with a test for divergence. If the test for divergence is inconclusive, we say, okay, is this thing a p-series? If it's not a p-series, we say, okay, if it's not a p-series, is it a geometric series? And if it's not a geometric series, now we're going to go over a couple more tests that we're going to do to really figure out what we got to do to figure out if these series converge or diverge. So I will see you guys in the next videos.